Now recall that we had our parameterization t theta t phi of the unit sphere using the spherical coordinates theta and phi. We calculated our normal vector t theta cross t phi, kind of a fairly long expression, that at the end we got t theta t phi equal to this. And we calculated the magnitude of t theta t phi, called that the magnitude of the normal vector, and that's off the screen over there. But we got the magnitude of the normal vector to be the magnitude of sine phi. Now, we're going to claim that the area of the surface is going to be the magnitude of the cross product of the two tangent vectors that we get from our parameterization over the parameter space. Now remember, okay, theta and phi, I want to find the surface area of the upper half of the unit sphere. So we can describe the upper half of the unit sphere in terms of this parameterization by 0 less than or equal to theta less than or equal to 2 pi, and 0 less than or equal to phi less than or equal to pi. And actually, now I want to go to pi over 2 because that's the upper half. We get the whole sphere if phi went to pi. Now remember that rho is 1 on the unit sphere, so that these are just polar coordinates, spherical coordinates, with rho equal to 1. This is a parameterization. Okay, this vector r equals rho sine theta cosine phi I, it's a little smudge now, plus rho sine phi sine theta j, plus rho cosine theta k, describes the unit sphere. And if theta goes from 0 to 2 pi and phi goes from 0 to pi over 2, it describes the upper half of the unit sphere. Verify that with your knowledge of spherical coordinates. Okay. This means that our surface area is going to be the integral of this magnitude of this cross product times d theta d phi, are integrated with respect to theta and phi. What are our limits on the integral? Well, theta goes from 0 to 2 pi, and phi goes from 0 to, didn't leave myself a lot of room there, but hopefully you can read that. Okay, so 0 to pi over 2, 0 to 2 pi with respect to theta and with respect to phi. Well, our theta integral is the first one. There's no theta dependence. The integral of d theta is just theta, and our derivative is just theta, so we substitute 0 and 2 pi. The change in theta is just 2 pi. So this becomes just 2 pi, which is a constant, so I take it out of the integral, times the integral from 0 to pi over 2 of sine phi d phi. I'm actually going to end up with the negative of the correct result, and I'll explain that in a minute and why we got the negative and what we could have done to avoid that. Integrating, now okay, I've replaced the magnitude of sine phi with just plain old sine phi. How can I do that? Well, our domain goes from 0 to pi over 2. Phi goes from 0 to pi over 2, and for every value of theta between 0 and pi over 2, sine phi has what value? Well, the value of sine phi is never negative. Okay, it's 0 when theta phi equals pi over 2, and it's positive for every other value of phi, so we don't need the absolute value sign. So we have this. And in fact, even if we went from phi equals 0 to pi to get the whole sphere, the sine phi would still be positive because the sine is positive for all values of phi between 0 and pi. Okay, so we never needed the absolute value sign in the first place, even if we went through the whole range of phi values. In any case, and you can verify this. Actually, I said we were going to get a negative and we aren't. I was being careless. Okay, and let me just do this step. Okay, antiderivative of sine phi is negative cosine phi. Evaluating cosine phi at 0, we get what? We get 1. Yeah, and evaluating pi over 2, we get 0. So we get 2 pi times 0 minus negative 1, which is 2 pi. Now, is this the area of the upper half sphere? Well, yeah, it sure is. I'll say that's the area of the unit hemisphere. And I assume it's common knowledge that the area of a sphere is 4 pi r squared. So if r is 1, the area of the whole sphere is 4 pi, and that the area of a hemisphere would then be 2 pi. This verifies the area formula for the area of a hemisphere, and thereby for the area of a sphere. Okay, so this works out. And all we did was we parameterized the unit circle in terms of an r vector, in terms of the parameters phi and theta. And then we found our t theta and t phi, but just by taking a couple of straightforward derivatives. We did the cross product, found the magnitude of the cross product, simplified it down to sine phi, and integrated that magnitude with respect to theta and phi. We didn't have to do a row, sine theta, cosine phi, all that stuff. We didn't have to do an area increment. We just used the parameters, right? Theta and phi, and that worked. Now, we can do the same thing with our tx and ty. Okay, so we can say also then that if what I'm telling you is true, that the surface area should also be equal to the double integral of the magnitude of tx cross ty dy dx over the values of the parameter here. Now, we're doing the hemisphere, so we're going to let x go from -1 to 1. And actually, yeah, we're going to go over the whole interval. We'll see how this works. Okay, what's the magnitude of tx cross ty? Well, tx cross ty is xi plus yj plus the square root of 1 minus x squared minus y squared over the square root of 1 minus x squared minus y squared. You can verify easily enough that the numerator has a magnitude that's x squared plus y squared plus this square root squared. Well, when you square that square root, you end up with just 1 minus x squared minus y squared. The x is squared, so that gets rid of the minus x squared. The y is squared. Add that to the negative y squared, you get 0, and you're just left with 1. So I'm just going to say, and you work it out, write it out in any way you need to. The magnitude of this vector here is 1. I'm sorry, the magnitude of the numerator, the vector in the numerator is 1. The denominator is just a scalar that can factor out so that the magnitude is 1 over the square root of 1 minus x squared minus y squared. So here is the integral. Now if you evaluate this integral, using your trig substitutions and so forth, it should be 2 pi. I'll leave that as a question for you to work out. I'd work it for you, but there are other things that have to get done tonight, and I just don't have time to explain that whole thing. Remember, for example, that if x equals cosine theta, then 1 minus x squared would be 1 minus cosine squared theta, which would be sine squared theta, so that the square root would just be a sine theta, right? You can do a similar thing with this integral, and if you want to look at the videos that I posted several years ago, you see me working through a lot of integrals of this type and doing it in detail. So I just don't justify doing it right now. I'd be kind of reinventing the wheel. And I've got to get these done right now. Okay, so verify that equals 2 pi. Take a lesson from this. Okay. Now there's one more, and I didn't do this in class, so this is kind of an expansion of what we did in class. Okay, I want to talk a little bit about the divergence theorem. I've got some stuff written up here, and we'll move to that in the next clip.